Our next speaker is a space architect, recently graduated from the International Space University, Ms. Helen Wexler. She's the founder of Bubble Bas, an aerospace startup developing technology for 3D printing and robotically assemble a Mars habitat. You should also visit the DMars project outside when you have the time. She is a graduate in architecture, graduate of Bezalel School from Jerusalem, and she's a lecturer in technology paradigms in architecture. Helen is named Forbes Israel 30 under 30 list of young innovators. Helen, come on.
It's an honor to be here today alongside such a distinguished panel of speakers and guests. Today, we're going to talk about one of my favorite topics, space manufacturing. So why do we want to manufacture things in space instead of just manufacturing them on Earth and sending them up to space? Well, for one, creating replacement components in space. Instead of carrying additional extra parts into space, astronauts and robotic spacecrafts could manufacture replacement parts as needed. This could reduce mission mass and help with emergency repairs. We see here in the picture, Made in Space, who 3D printed a wrench when one of the astronauts on the ISS misplaced their wrench. But this could be beneficial technology for other things as well, even things like 3D printing ceramic reentry panels on a spaceship that was damaged in space, or many other applications. Another reason we want to manufacture things in space is to build structures that are difficult to create on Earth or to just transport in launch vehicles. Because currently, almost all spacecraft designs must fit into rocket fairings and survive launch stresses. That's a lot of vibration. If manufactured in space, structures could be larger, lighter, and tailored to the zero-gravity environment. This really would enable us to create more fragile, delicate structures if we're creating them on orbit, because we can send the filament up into the International Space Station or other places in space and then fabricate it there. Another reason for space manufacturing is recycling in space. Astronauts could recycle some of their garbage, such as equipment packing material, into new parts. Tethers Unlimited developed this machine, which recycles plastic waste from cargo boxes during resupply missions and actually spits out plastic printer filament that can then be used on board the International Space Station 3D printers. Another application for space recycling is repurposing retired satellites and using this space junk for robotic spacecrafts. And my favorite application is the use of resources on planetary surfaces, in situ resource utilization. So facilities on asteroids and the planetary bodies could be manufactured using local materials, reducing the mass which must be sent from Earth. So as we think about building things in deep space and building larger things, this becomes more and more critical. So everything from landing pads, launch pads, access roads, radiation shields, structural trussers, and yes, even houses one day. If we're able to use local materials, this is going to make it a lot easier and more cost-effective. And just yesterday, astronaut Jean-Jacques Favier mentioned his research on the field of using lunar regolith simulant to 3D print solar panels. So these are the types of innovation which are really going to allow us to create bigger structures in space. So I got interested in space when I was an architecture student here in Israel at the Bezalel Academy of Art and Design, and I was really interested in the new frontiers and the urbanization of what it would look like if we had a society on Mars. But this was very much a theoretical architectural project. But through this, I started learning about Martian geology and thermocycling and all of the challenges of fabrication and creating a habitat in space. on Mars specifically. And as I was working on this project, there just happened to be a call for proposals from NASA for the 3D printed habitat challenge. So I joined forces with my engineer friend Lior Aharoni, and we submit a proposal to NASA. So while most of the other teams submit technical proposals, we submitted a comic book. So it's a pretty technical comic book, and we explain here how we bring a high-performance inflatable bubble to Mars, and because of the difference in atmospheric pressure, we're able to inflate it and then fill it with solar-sintered sand. And then we create a solar-sintered brick dome with a swarm robotic technology, again, because we want to have that redundancy when we're talking about deep space. So having collaborative robots work together to build the dome to create an additional layer of protection from radiation and from micrometeoroids. So this was the initial proposal. 160 teams from around the world submitted proposals to NASA, and 30 were invited to present in New York. In this part of the competition, my team won an honorable mention. The next phase of the competition was material science. And for this part, we started working with Hebrew University, with Professor Shlomo Magdassi and Dr. Michael Liani, in developing basically a new ink for the 3D printer that's based on local Martian materials and doesn't use polymers, right? Because if we're talking about sending things to space, we want to try and avoid using polymers because we don't have those on the surface of Mars. And so, very close to the deadline of the NASA competition, our printer broke. But we were so determined to participate in this competition that we actually borrowed this robotic arm from the importer of robotic arms into Israel, and we borrowed a pasta machine and used the pasta machine for the extrusion function of the 3D printer. So basically, we fed our Mars dust recipe into the pasta machine and used it to print the thing. So as you can see, the printing resolution isn't amazing because, well, we used a pasta machine. But what was amazing was that the material performed really well in ASTM compression tests and significantly surpassed the NASA-required minimum for the competition. So since then, we've continued developing our technology, developing our printing methodology, the curing, and the material science behind what we've been working on. And these days, we're gearing up for phase 3 of the competition. So we have 5 deliverables over the next 16 months, ranging from BIM CAD design through 3D printing and building foundation, hydrostatic testing, and the most complex, in April 19th, is to actually 3D print and robotically assemble a subscale habitat. So that will be 10.5 square meters. We hope that we'll be successful in moving forward to phase 4 in the NASA competition, where we will then be tasked with printing a 94 square meter full-scale habitat for 4 astronauts. These days, we're working on developing our team, expanding our team, and I invite anyone, both from academic and from industry, who think could be relevant to work with us to come talk to me throughout the conference. But it's not all sunshine and rainbows in the land of space manufacturing and 3D printing. There are some challenges, such as zero gravity, vacuum, and thermal effects. The lack of gravity atmosphere removes familiar constants of ground-based manufacturing, which is challenging. But it might also allow for some new innovative techniques, such as printing from several directions simultaneously. Drastic day and night temperature fluctuation can warp physical dimensions and change cooling rates, and will have to be accounted for in the design of 3D printing equipment. Another challenge is qualification and certification. Space hardware must be built to rigorous standards to accomplish complex operations in harsh environments with limited opportunity for repair. Currently, the methodologies to guarantee the quality and performance of 3D printing parts is still lacking. Another big challenge with this technology is power. On a spacecraft, electricity is an expensive commodity. often available in limited and fluctuating amounts. Multiple 3D printing units, especially those using high-energy techniques, could stress the power supplies of many current spacecraft designs. And lastly, automation. On the ground, 3D printing relies heavily on human presence for setup, support, post-processing. While crewed space missions can rely on human operators, robotic missions would need to fulfill these parts of the process autonomously. And I'd like to leave us with a quote from Robert Goddard, who invented the multi-stage rocket and the first liquid fuel rocket. "It is difficult to say what is impossible, for the dream of yesterday is the hope of today and the reality of tomorrow." I hope that you share my excitement for the reality of tomorrow in the field of space manufacturing. Thank you.